Okay, in this video, I'm going to show you guys how to use the that and then the uncle to help us to get the series expansion for x times e to the x, and also its inverse, so we'll end up with the Lambert W function. The that Taylor will help us to get the original, and then the uncle Lagrange will help us to get the inverse. As you can see, we put down the formulas right here already. In this video, we'll just work them out. And the proofs for these two formulas, maybe later on. Alright, anyway, thanks to the that Taylor, f of x is equal to the series as n goes from 0 to infinity. And this right here is the nth derivative of the function f. And by convention, the zeroth derivative is just the original function right here. And then some number a, and then divided by n factorial times x minus a to the nth power. And notice that right here, this a, it's actually the same as this a right here. And for simplicity purpose, because I just want to demonstrate how this two formula works, I will pick a to be 0. So I will just put down a is equal to 0, and of course, it's the same a right here. Now, I will have to figure out this right here. I will just have to differentiate x times e to the x n times and look for a pattern. And the good thing is that I did a video on that already, so go check that out if you need to. Here, I will just write it down for you guys. So, when we have the nth derivative of that function, let me just put on x first. This right here, we actually end up with x plus whatever this n is, and then times e to the x power like that, right? And because, as I said, a is equal to 0, I will just plug in 0 into here and here and here. So we see that the nth derivative of the function at 0, well, 0 here is just 0 plus n, and then e to the 0 is just 1. So all in all, we'll just end up with n. So that's pretty much it. Now, we'll see that f of x, which is that, let me just write it down, x times e to the x, it's equal to the series as n goes from something to infinity, right? There's a reason why I haven't put this down yet. Anyway, let's write this down right here, which is the nth derivative of f at a, which is this right here. I have n right here, and then on the bottom, I have to divide it by n factorial, and then x minus a, but a is 0, so we just have x to the nth power like that. Now, here is the deal. As you can see, this is n factorial, which is like saying n times n minus 1 and a factorial. I can cancel out the n, so that's good. But the problem is that when they cancel this out, the n starts actually at 1. Why? Because the first term was 0. Because the value of the function when x is 0, when a is 0, is 0. So the first term is when n starts at 1, right? So when you cancel it out, you see that you will have to just let n goes to from 1 to infinity. And you have this expression. So this is legitimate. And sometimes you can also just fix the index if you would like. Well, if you really want to have n start at 0, what you are going to do is you are going to subtract 1. So you get n is going from 0, and let me put this down in red just to emphasize. And then infinity minus 1 is still infinity. When you do that, well, to balance things out, right here, you will have to add 1 to the n. So you end up with 1 over n plus 1 and then minus 1. So you get n factorial here now. And then you add 1 to the n, so you actually end up with x to the n plus 1, like that. So this right here is for x times e to the x. In fact, another way to do it is you can look at the power series of e to the x at 0, and then you will see it's just the sum when n goes from 0 to infinity, 1 over n factorial times x to the nth power, and then you multiply by x. So you get plus 1 right here. That's a quick way to do it. But I just want to show you guys how to utilize this formula right here. So we are done. This is my series for that. Cool. Now, the main dish is here, the uncle. Lagrange. This is called the Lagrange inversion theorem. Well, you really cannot write Lambert W function as like elementary functions. But in fact, you can still find a good looking expression for the series expansion for that. Even though the answer right here will be in terms of y, but don't let the y bother you. Or if you really want, you can look at this as w of x and then differentiate the Lambert W function and use that to help you out. We can actually differentiate the Lambert W function because I did a video on that, but you have to look for a pattern. Good luck with that. Leave a comment down below and let me know how that goes. I'll leave that to you, okay? Anyway, let's use the uncle to help us out. In this formula, we see a lot of a's, and the good thing is that a is still 0. So let me write this down. A is still 0. As you can see right here, this is the most difficult part. Not only you are differentiating, you have to do it n-1 times, and you have to take the limit as well. Anyway, here we go. Let's look at this. We have f of a. A is 0. That means I have to plug in 0 into my x here and there. So the good news is that f of 0 is also 0. So I think the 0 will be really friendly, right? All right, now let's just work this inside out. I start with y on the top, minus a, which is 0, so minus 0, nothing there, divided by f of a. This right here is the original. I have to plug in y into the original here and here. So that means I get over y e to the y's power like that. Not done yet, because I have to take this expression raised to the nth power. So I have to look at this and then raise this to the nth power like that. Not done yet. This right here is just an expression because we still have to take the derivative. So I will do this, and then I will have to differentiate this n-1 times with respect to y, of course. Alright, so this is pretty much the story, alright? And now we just have to do the work. Well, let's see. Is there any way for us to simplify the inside? Yes, y and y cancel. Inside, it's at e to the negative y raised to the n power. So inside, it's saying e to the negative ny power. And then please differentiate this with respect to y n-1 times. So how does this work? Well, imagine you have e to the n, e to the negative ny, so this is just a constant multiple of that. Like it doesn't matter how many times you differentiate, you always get e to the negative ny back, right? But you have to do this n-1 times for the derivative. That means you have to use the chain rule n-1 times. Each time you have to multiply by negative n. Well, when you differentiate this n-1 times, you will have to multiply by negative n-1 times. So it's like this, right? So the derivative of this is that when you do it n-1 times. So that takes care of the inside. Not done yet. We still have the limit right here, huh? So let's see. I will have to take the limit as y goes to 0 like that. Good news, because this is continuous. When you plug in 0 into the y, you get e to the 0's power pretty much, and you just have that back. So the answer is what? All this gives you just that, namely negative n raised to the n-1 power, like that. And I think I should have some space for the dash, so let me just make it cut like this. Okay, now let's see. This right here will go here. And the good news is that that's pretty much it. Wow, okay, cool. Now, here we go. The inverse, which is the w, right? The Lambert W function. And the input right here is y. So I'll just put down w of y. Thanks to the uncle, it's equal to a, which is 0. And then we have to have the series. Let me just put this down. When n goes from 1 to infinity, on the top, this part is that, right? The blue portion that we did, which is negative n to the n-1 power. And if some people are picky, you can look at this as negative 1 times n. So that's like saying negative 1 to the n-1 power times n to the n-1 power, depending on which one you prefer. I think I'll put on this right here. So the top here, I get -1 to the n minus 1 power, and then times n to the n minus 1 power. And then divided by n factorial. And then multiply by, well, y minus f of 0, which is just y. So I have y raised to the nth power. So I just write down the n right here. And in fact, this is it. If you want to fix the index, up to you. Up to you, right? Seriously, if you really want that, sure, why not? Because I fixed it right here. I should also do it right here, huh? So just for practice. So if you do that, I will subtract 1 here. So n goes from 0 to infinity. I will have to add 1 to the n. So here I get -1 to the nth power because I add 1 here already. Likewise, don't forget to add 1 right here for the base. I have n plus 1 to the nth power. Minus 1 plus 1 is just that. Over n plus 1, right? And then you have the factorial. And then y to the n plus 1 power. This right here is the series for the Lambert W function. Of course, this right here doesn't mean anything if you don't have the radius of convergence. So I will tell you. The good news right here is that the radius of convergence is infinity. Unfortunately for this one right here, it's not as good. Either one, okay? The radius of convergence is 1 over e. Yeah, it's a tiny bit. But anyway, it's cool. And of course, you guys can watch my other videos. I'll show you guys how to use the ratio test to get the radius of convergence. But I think this is super amazing, right? So check out the dad and then the uncle on the back of the shirt. And you guys can also leave a comment down below because I forgot to put the mom on the shirt. Let me know if I should include the mom somewhere or not. But yeah, I will wait for your comments. Anyway, hopefully you guys all like this video. It took me a lot of times to prepare this, so please give me a like. And then if you're new to my channel, please be sure to subscribe and also share this video with the people that you think that they also might like math. Thank you guys so much. As always, that's it.